Today we are going to start talking about a new theorem called Rolle's theorem. And what Rolle's theorem essentially says here is if I have 2 points, right? So I have A f of A and B f of B, and they have the same y coordinate, right? They're on the same horizontal line here. And so that means that f of A equals f of B. Now you can kind of see over here that my points are technically 2, 4 and negative 2, 4. So their y coordinates match. And what Rolle's theorem says is that if f of x takes on the same value at 2 different points at A and B, meaning their y values are the same, then somewhere between these 2 points, the derivative is 0. So basically, graphically, what that means is if the secant line between x equals A and x equals B is horizontal, then at least one tangent line between A and B is also horizontal. Okay. So what it's saying, okay, so first of all, we want to draw something that is continuous and also differentiable. So what that means is if I have these two y values and they're on the same horizontal line, then if I try to connect them somehow, then somewhere the derivative will be equal to 0, right? The slope of the tangent line will be equal to 0. Now the most trivial case is essentially where it actually is a horizontal line, right? This is the line y equals 4, and if I do the derivative of y equals 4, my y prime is equal to 0 all the time. So in this case, like, it's true all the time. Everywhere between A and B will take on these horizontal values. So here's a non-trivial example where I have y equals x squared, right? So I'm connecting my A and B, they have the same y values, and somewhere in between these two values, A and B, my horizontal line, or my tangent line will become horizontal. You know, really the premise is basically if the straight line between these two is, if the slope of this line is 0, then somewhere along between A and B, my tangent line will become 0. Or essentially, if the tangent line is also 0, then that means that those two lines will be parallel. So let me animate my tangent line here. So you can kind of see right there for a second, right? It takes on my 0 tangent line, okay? It's kind of interesting how it like floats around there, but let's stop this and put it where it is, right? So right here at x equals 0 is where my slope of my tangent line, right, is equal to 0 because my tangent line is horizontal. So that means that's where my slope of my tangent line is 0. And also you notice that it's parallel with our original line between those 2 points, okay? So let me change that. What if it's not below? What if it's above? It's basically the same case, right? So there's my new line. Now I've called that one G, so let me change my tangent line to G, so it'll do the same thing. Of course, I have it set up right there is actually where it's 0, but let me animate it just for fun. You can kind of see that between there, it does in fact take on a 0 slope, which is horizontal to my original line here. And so let's go back to, I should have moved it before I changed it, but it's right there, right? So right there between A and B, in our case, A is negative 2, B is positive 2, so this is at x equals 0, which is between negative 2 and positive 2. So again, I've shown that somewhere in between them, like I can't draw these two lines and connect them without ending up with basically a peak or basically a valley somewhere. And then my last case is, what if it's more than 1? Well, that's fine because it just says that there's at least 1. Okay, so let me change both of those to H. And let's animate this. So this one is actually going to have 2, right? So there's one real quick, and there's one again. Okay, so let's pause this for a second, and we can move it ourselves. Right, so actually right about, oh, can I get there? This one's not perfect for me. So it kind of looks like 5, 5 maybe. There we go, I got it horizontal. So there's one place where it's horizontal. And let's see, where's the other one? So let's drag our A to, oh, actually, wait a minute. I'm going to have to move this A here to the bottom here. And there's my other one. It's at a weird spot, so let's see, let me put on 5, 5, does that, yep, that makes it perfect. Okay, so there's my other horizontal. And you notice, again, like the whole, it's like it's parallel to the original, like this is the secant line between A, f of A, and B, f of B. And this line is parallel to it in between A and B, okay? So this is the whole idea of Rolle's theorem, is basically that if my two y values match, now this book, for some reason, almost all of their examples, they come out where f of A and f of B are both 0. That does not have to be the case. The only thing that has to be the case is that f of A and f of B have to match, right? So that the line between them is horizontal, not that their actual values are equal to 0. So I just wanted to point that out because the book is really kind of a little bit unclear about that. I also want to make a point that my one last example, so let's take all of these off of here, and we're just going to look at this one here, okay? Now this one here is not, right, so this is actually a place down here where my derivative fails to exist. Let me call this something else here. Let me call this m of x, and see if I can make this animate here. M. So in this case, now my function really needs to be continuous and also differentiable, because you can kind of, maybe, can I get it to, oh, I got to put the line on there. There we go. Let's put the line on there. Right? It doesn't actually ever get 0. It's always just like laying on this line, or when I get here to 0, it lays on this side. It never really takes on that horizontal, even though that's a low point on there. So that's a place where the derivative doesn't exist, and it doesn't fit Rolle's theorem, and also Rolle's theorem fails. Sometimes I can have a place that isn't differentiable, but maybe I can still find a place in between A and B where it is going to be horizontal, but not in this particular case. So for Rolle's theorem to apply, it has to be both differentiable between A and B, not necessarily at A and B, but differentiable everywhere in between. So the open or the closed, it has to be continuous on the closed interval, meaning it has to be continuous at A and B included, right? But it has to be differentiable on the open interval. So if it's not differentiable at one of these endpoints, that doesn't matter as long as it's differentiable everywhere in between the points. Okay, so let's do some examples on paper. So here is our formal definition of Rolle's theorem. We're going to let f be a continuous function in AB, meaning the endpoints are included here, and differentiable on the open interval from A to B. So it's okay if it's not continuous on the endpoints or differentiable on the endpoints, but it does, it has to be continuous on the endpoints, not differentiable on the endpoints, but everywhere in between. And we also have y values that match, that f of A equals f of B. Then there is at least one c between x equals A and x equals B, such that f prime of the c is equal to 0. Okay? So we're going to essentially verify the criteria met, that the criteria is met for Rolle's theorem, and find a c such that f prime of c equals 0 in the interval. So the primary thing for Rolle's theorem is that f of A equals f of B. Now this is A, right, and this is B, so this is not a point, this is my two x values. So I want to show first, I'm hoping, that f of negative 3 is equal to f of 1. So that's the first thing that I need to show, is that this up here is true, that f of A equals f of B. Okay, so I'm going to plug in my endpoints. F of negative 3 gives me positive 9 minus 6, which is positive 3. F of 1 gives me 1 plus 2, which is also 3, so that part has passed. Okay. Now I do know that x squared plus 2x is a polynomial, which should be nice and smooth and differentiable everywhere and continuous, so I don't have any discontinuities, or I don't have any non-differentiable places. So this should hold, so let's find it. So basically what we should find is that we should be able to find where f prime of x equals 0, so let's do f prime of x here. So f prime of x would be 2x plus 2, and we're going to see that this is equal to 0. And what should is that we should find that this is equal to 0, this x value, when I solve for it, should be between -3 and 1. And if I move my 2 over here, I get -2 equals 2x. And in fact, I get x equals -1, which is in the interval from -3 to 1. So I have verified, right, that f of -1 is equal to 0, which is in the interval between -3 and 1, right? So I've shown it. So it did apply. My endpoint or my y values were the same. So that meant that somewhere between -3 and 1, I should find that my 0 or my derivative was equal to 0. And I did. I found that that was at -1, which is in between -3 and +1. So let's do one more example like that. All right, so this time we want to show that f of x equals x plus 1 over x is also meets the criteria between 1/2 and 2. Now I do notice that I'm going to have a discontinuity here at x equals 0. However, since 0 isn't in my interval, it's nice and smooth and continuous between 1/2 and 2, so I don't have to worry about that. So let's see if our endpoints do in fact match to make sure that we're doing the right thing. So if I plug in 1/2, I get 1/2 plus 1 over 1/2, and when I simplify this, this actually ends up being 1/2 plus 2, which is 5/2 fractionally. And so if I do the same thing with 2, I plug in 2 this time, I get 2, and then I get plus 1 over 2, which is 2.5 immediately, which is also 5/2. So I've shown that f of a equals f of b. So that means that I should be able to find a place where f prime is equal to 0 and an x value between 1/2 and 2. So let's do that. So f prime of x is equal to 1, and then let me rewrite this as x to the -1, just in case you've forgotten. And so the derivative of that would be -1 over x squared, right? -1 x to the -2, which is written like this. So I'm going to 0 then. All right, so I'm going to add 1 over x squared to the other side. I get 1 over x squared equals 1. And so if I have this, right, then I can think of this as 1 over 1. So basically if I flip it over, I get x squared is equal to 1 because I also have 1 over 1. So that means that x equals plus and minus 1. Now I don't really care about the -1, right, because that's not in our interval and it would be discontinuous somewhere in between there. But the x equals 1 doesn't work for me, right? F prime of 1 is equal to 0, and 1 is in the interval from 1/2. Okay? So there we go. All right, so let's use Rolle's theorem one more time. A little bit more interesting than just verify that it works. So we're going to prove that f of x equals x to the 5th plus 2x cubed plus 4x minus 1 has precisely 1, 0. So we're going to go back a little bit. So first I need to show that it has 1, 0. Now I don't need to find the exact one. It just says precisely 1, 0. So I'm going to go back and pull out the intermediate value theorem here. And so basically the intermediate value theorem says if I can find one y value, like assuming that this is continuous, which it is a continuous polynomial, that if I can find a y value that's bigger than 0 and one that's smaller than 0, then there is in fact a 0 somewhere on this function between those two. So let me just use f of 0 for instance. That'll give me -12, so that's my negative value. Now, if I try f of 1, I don't think that that's quite positive yet because I'll get 1 plus 2 plus 4, which is 7, so that's still negative. So that's still -5, right? So then if I plug in f of 2, then that's really going to, so then I have, so x to the 4th is 16, then times another 2, so that's 32 plus 2 times 8 plus 4 times 2 minus 12, and without doing the actual calculation, I know that that's definitely greater than or equal to 0, right? Because these are all positive values, and I'm just going to subtract 12 at the end. So I know by intermediate value theorem, by VT, that there is a 0 in the interval from 1 to 2, right? Because it was negative here and positive. Basically, somewhere between when x is 0 or between x is 1 and x is 2, my function does in fact take on a 0, okay? So I've showed that there's 1. So how am I supposed to use this to figure out if there's another one? Well, Rolle's theorem says, essentially, so that means if I have 1, 0, right? So this gives me a 0 between 1 and 2, right? So if I say 1 and I don't know where it is, I'm just kind of putting it somewhere in the middle. That if there's another 0 on here, right, then that means it's somewhere else. I don't know where it is. I'm just going to put a second line on here. But that basically means that if these 2 points are connected, right, then that must mean that my derivative takes on 0 somewhere in between. So let's look at the derivative for a second. So I have f prime of x is equal to, here's my f, so 5x to the 4th plus 8x squared plus 4, and then the 12 drops away. So this is my derivative. Now this is, right, this is x to the 4th and this is x to the squared. When I put negative values in either one of these, they'll never take on a negative value, right? Because if I put in -1, it's going to be the same thing as if I put in +1 because I'm going to raise it to the 4th, which will make it positive. And the same thing with any negative number. In fact, the smallest value that I can make this take on is that if x is equal to 0, then I get out +4, which means that I can't make f prime of x equal to 0. Right? It's just not going to happen. I just can't make it. And if I try to, right, I'm never going to get a negative number, right? Because no matter what, even if I put in fractions, they're still going to be positive. They'll get smaller, but I'm still never going to get 0. And so because I can't make this equal to 0, right, and Rolle's theorem says that I could if there's another one, then this means that there's only 1 0, that there's precisely 1. So this tells me that I've only got 1 0 because Rolle's theorem tells me my derivative can't be equal to 0, and Rolle's theorem says I would be able to make that 0 if there was another one. So basically we've shown that there is precisely 1 root here. Okay? All right. So we will talk about the mean value theorem next.